Okay students, let us try to solve this question. What transition of hydrogen spectrum would have the same wavelength as the Balmer transition from N4 to N2 of helium spectrum? Okay, so let us try to solve this question. It goes like we know that for hydrogen like particle, in general we have a formula which can be written as nu bar, or which is equal to 1 by lambda, which will be equal to r z square. Rydberg's constant is r. Z there stands for the atomic number, then 1 by n square minus 1 by n square of the final stage. This formula we are known. Okay, so therefore for helium plus spectrum, that too given in the question is for Balmer series, that is from N4, right, to your N2 level, orbit 4 to orbit 2. Here Z for helium we will be taking it as 2, and N initial we can take as 4 because transition is carried out from 4 to 2, and your N final we can take it as 2. So let us put this value in the above formula which I have stated. So 1 by lambda will be equal to your r into Z is 2, so 2 square, and 1 by N1 is your 4, so it is 4 square, 1 divided by 2 square. So I have just put the value of Ni and Nf orbits in this particular formula which we know generally given for hydrogen like particle. So just let us try to solve this. This gives you r into 4, 1 by 16 minus 1 by 4. On solving this, you will get r into 4. This you can take LCM, which you will get 16. This becomes 1 minus 4 4s are 16, 4 1s are 4. So here you can cancel it off, 4 4s are 16. So you will have r, and in the bracket you will have 1 minus 4 will be minus 3 divided by 4. So this ultimately what you are having is minus 3 by 4 r is the value of 1 by lambda. Okay, so this you got it for helium spectrum. Now the question says that this particular value of lambda which you are getting should be the same for your hydrogen spectrum, and in that case at which transition this would be same. The wavelength would be same at what transition in case of hydrogen spectrum. Okay, so now for hydrogen spectrum we will try to solve this. For hydrogen spectrum, what we need to do is, the formula remains the same. 1 by lambda is equal to r z square, 1 by initial square minus 1 divided by n final square of the orbit. Now here for hydrogen spectrum we need to find out that this value of 1 by lambda has to be same as minus 3 by 4 r. So here we need to do this by trial and error method. So let us try to take the value of your n1 as 2 and n final as your 1, and let us try to solve this putting in this equation, and let us just check, are we getting the answer as minus 3 by 4 r? Okay, so let us continue. 1 by lambda will be equal to r. Here we are talking about hydrogen spectrum, so it would be 1 square, and 1 divided by initial is your 2, so 2 square minus 1 by 1 square. Solving this further, you will get 1 by lambda is equal to r. In bracket you will have this 1 1s will be 1, and in the bracket you will have 1 by 4 minus 1. So solving this further, you will get LCM, you take 4, you will have here 1 minus 4. So ultimately you are getting 1 minus 4 would be minus 3 by 4, and this r. So you can see that what we have done is we have got this value same by taking your n initial as 2 and n final as 1. So the wavelengths now would be same. for which transitions the wavelength would be same, that they were asking in the question. So with what transition in the hydrogen spectrum would be having the same wavelength, okay, as the Balmer transition. So for Balmer transition from 4 to 2 we have found out 1 by lambda is minus 3 by 4 r, okay. So now they were asking, now this wavelength would be same for hydrogen spectrum for what transition. So we have just tried to put N1 and Ni and NFS2 and 1 and we were getting the same value, and hence we can say that finally we can say that, so the wavelength, we can say, so the wavelength of transition of hydrogen from N2 to N1 is equal, that is what they were asking, no, is equal to transition of He plus from N4 to N2. Okay, so this is the solution for your question number 33, and the conclusion for it is what transition of hydrogen atom they were asking. So we have seen that the transition from 2 to 1 was giving you the same wavelength for Balmer transition from 4 to 2 of helium spectrum and of the hydrogen spectrum. I hope you all have understood, and you can just have a look at a glance how the solution is there for done for this particular question. Thank you.